In this video, we'll be trying to understand a bit better how rainbows work. So first of all, we want to get some intuition about how they work, and then maybe we can obtain some constraints as to the specifics of the mechanism. So when rainbows are one of the most commonplace phenomena that exist, so it would be nice to have some appreciation towards them. So we know that it has to do with refraction of light from the droplets. So the most logical thing to do is to start by designing a droplet. So we will assume that the droplet will be spherical in shape. So we can start by having a circle, just for simplicity. So this is a crudely drawn droplet of raindrop. And we want to see, first of all, I'm going to make a line just for reference for my own sake. So the mechanism that we propose is that there will be some sunlight from some direction, and then the light will come in and it will intersect the back of the droplet at some angle beta. So it wouldn't make too much sense to consider what happens if the ray exits from this side, because if the observer is here, then he would be blinded by the sun coming from the direction. So it doesn't make sense for us to look so much on this direction. So we have to consider another mechanism for that. And the most intuitive, potentially, or the simplest case we can think of, would be when there is some form of reflection on the back. It doesn't even have to be a total reflection. A small amount of that beam can actually just be reflected to the back. We know that this angle has also to be beta, since it's a reflection. And again, I'm going to just draw a few more lines, just for reference. And it will exit at some other angle phi. We don't really care about the specifics of that. So once again, we have the incoming beam, like so, again at some angle phi, and here we have it. So now, this now makes much more sense, it's much more intuitive, because if our observer is now here, then the sun is no longer in his eyes. So in such a case, we would be able to observe this kind of phenomenon of a rainbow. So now let's go a bit more into the specifics. So when we talk about refraction, which is a phenomenon involved, we typically think of Snell's law, and that would be the first thing that maybe we should start by writing down. So Snell's law dictates that if you take the refractive index of the medium at which the incident beam is in, so in this case is air, times the sine of what we will call theta air. So this is the angle at which the incident beam arrives on the normal with respect to the surface. So the normal to the surface would be something like that. We know that it has to pass through the center of the circle. So this is now what we call theta air. And this has to be equal to the refractive index of the new medium, which is water in this case, times the sine of theta w. And theta w is nothing more than the angle with respect to the normal inside the new medium. So this is now what we call theta w. And that's pretty much it. That's pretty much all you need to know about the mechanism inside the droplet. But now we need to understand how things are connected with respect to each other. So in this case, for example, we need to understand what the value of this is and what the value of this is. So theta w is very simple. It has been reduced to a very trigonometric issue. So we can assume a triangle between this point, the center of the drop, and the point of reflection. And we know that this has to be an isosceles triangle. And hence, if this angle is beta, then forcefully that angle has also to be equal to beta. So here we have our first constraint, that theta w has to be equal to beta. So beta, again, is just an arbitrary parameter. It doesn't have to be specific in the beginning. We don't need to plug any numbers whatsoever. This will happen all the way in the end. We start with an abstract idea first. So the second constraint of theta is a bit more complex. But if we are lucky, we can notice that this angle, let's call it y for simplicity, has to be equal to this angle here, y. Because we notice that this line and this line are parallel to each other, and they're connected by the same line. So now it's just boiling down to basic trig. So if we call this angle here x, we know that in a semicircle, the semicircle is comprised of 180 degrees, so from here to here is 180 degrees. So y plus x have to give you 180. So here's the first linear constraint. And now we have another condition from trig, which is just related to the sum of the angles in a triangle must be equal to 180 degrees. So we have one angle here, and one angle here in this isosceles. We know that theta w has to be equal to beta. So once again we have beta plus x must be equal to 180 degrees. So we have again x plus 2 beta is equal to 180 degrees. And now we can simply just take the difference between those two equations and we end up with y minus 2 beta is equal to 0, or y is equal to 2 beta. So that's another constraint as well. So what we can see here is that y is comprised by theta air plus phi. So theta air would be simply y minus phi. So we can now from here say that theta air must be equal to 2 beta minus phi. And here is our second condition. Here is condition number 1. And here's condition number 2. So now we have everything we need to know about the equation. And the only thing we need to do, what is left to do, is to simply plug things back. We have then n air times sine of theta air is equal to n water sine theta water. So the refractive index of air is 1, so that simplifies a lot. Theta air we know is equal to beta. The refractive index of water for the optical spectrum is very close to 1.3, 1.34, something like that. So for my own simplicity, I'm just going to write it as 4/3, something like that. The reason it's not quite specific is because it's wavelength specific. So the wavelength of light that reaches the droplet will be refracted at a different angle. So it's approximately about 4/3 for all purposes that we care about. And theta w is being given by 2 beta minus phi. So we just now simplify the expression to sine. Oops, sorry, I made a mistake. No, yeah, sorry, these are the other way around, my bad. So I'll fix that here. So it's 2 beta minus phi is equal to 4/3 sine of beta. And now I can take the arc sine on both sides. And all the arc sine does is simply to alleviate the sine function. So we end up with 2 beta minus phi is equal to the arc sine of 4/3 sine beta. And we can further reduce this to phi is equal to 2 beta minus arc sine 4/3 sine beta. So this is great now, because we have an angle, which is it's the exit angle at which, with respect to the ground, with respect to us essentially. So this is something that we care about, and it's connected to beta, and exclusively beta, which is some angle related to the internal mechanism of how refraction works inside the droplet. So this is pretty much all we need. So now it's something a bit more interesting, is that it matters at which angle the light will enter into the droplet and exit from that. So we need to find what's the most probable value of beta that would be in play in real life. And the easiest way to do things is to either plot this function as a function of beta, or you can simply take the derivative with respect to 0. So if you were to plot the function, you would find out that it looks something like that. And it literally stops in midair almost. And it has a peak value of something close to 40 degrees and a maximum at something close to 21-ish degrees. But the derivation is very simple. You just need to take the derivative of the function phi with respect to beta and set that equal to 0. That will give you the maximum of the function. So the derivative of 2 beta with respect to beta is 2. The derivative of an arc sine is one of those functions that you really have to remember how to do things. But I happen to know that it's given by 1 times the square root of 1 minus the argument. The argument is this, so I just have to square it. 4/3 sine beta squared. And then it has to be timed with the derivative of the argument. So essentially it's the derivative of this, which is 4/3 of the cosine. And set that equal to 0. Then there's a bit of algebraic manipulation. It's not really much to worry about, but you can actually show that this gives you beta max at square root. Sorry, it's something close to 0.7. That's in radians, so you have to be careful about that as well. Units do matter in physics. And if you were to convert that into degrees, it will end up being something close to 40.2-ish degrees. So if you plug now that value back here, that will give you the optimum value of phi that you would expect. And you can actually show that phi max is something close to 21 degrees. And that's it. This means that nature has a preferred way of working. This tells you that water droplets have a preferred angle at which they scatter light back, and that value is declared 21 degrees. This is what nature prefers to do. So if we now think again what really happens, so here we have our observer, here we have the sun, here we have sun cloud which rains, and we have all those droplets over here. So the sun comes this way at some angle, and you can consider the rays all the way like that as well, coming from the sun. So what it's telling you is that with respect to the ground, that angle is 21 degrees, and when it reflects back into your eye, that will have to be 21 degrees as well, so a total of 42 degrees. So the interesting part about this is that it's the phenomenon of the rainbow is dependent exclusively on what time of the day it is. Depending on whether it's noon or whether it's on the sunset, the height of the rainbow will be much larger. And then there are more questions about what happens if you have other rainbows. You can have double, triple, and so. And it's just a matter of how many times the beam of light actually reflects on the inside of the droplet. And well, that's pretty much it.